Hello, am I audible? Kshitij, are you there?
Yeah, you are.
Yeah, hi, you're audible.
I wasn't able. Okay, I wasn't able to hear you. Okay, no problem. So, good afternoon, everyone. It is a pleasure to welcome everyone to today's event, a guest lecture on Android internals and security. Today, we have Kshitij Gupta, one of the best firmware engineers from Teracube, a smartphone company based in Redmond, Washington, aiming to create sustainable mobile phones with a 4-year warranty. Kshitij Gupta here has a diverse portfolio and possesses a lot of experience in this field, having started hobbyist development tinkering since grade 10, working on a variety of Android devices on both platforms Qualcomm and MediaTek, and is widely known for his work on the Redmi Note Pro, where he was the first person to get everything working on a custom OS on a completely new and unexplored platform. Fun fact, he is also the person who made the first ever open source dark mode on Android.
Okay.
Right. Kshitij.
Yeah, hi guys. That's a lot of you. It's great to see. Um, First off, guys, I'll be honest, I'm not great at presenting. So if I stutter, please don't hold a knife to my neck. Like I'm trying. So today we're gonna talk about Android device security, and so we'll see what Android device security actually is, how it differs from other security things that are to do with Android. And yeah, I mean, let's dive into it. If there's no one else joining, I guess we can begin. So why should you listen to a dunderhead like me? Honestly, that's on you. I can't control that, but I'll tell you who am I. As Gagan mentioned, I'm a firmware engineer at Teracube. I finished my CSE in 2021 from Manipal University, Jaipur. I started a project called POSP, which is the most unserious fork of AOSP, which is Android and its open source nature. I've worked on several MediaTek and Qualcomm platforms. They're all listed based on the ones I worked on first, and the one at the end of the list is the one I'm working on currently, or I worked on last. So yeah, take it how you want to take it. If you want to listen to me, listen to me. You don't want to listen to me, that's fair enough. So goals of this presentation, we'll understand what device security means here. When we talk about security, we need to understand how the device starts up, and then we'll explore how the device actually gains trust on the code it executes. So we'll be seeing the fundamental boot process and how root of trust is maintained in this boot process, and we'll discuss on what happens when root of trust is not present. And we'll also look at the common Android and Linux security measures that are common to all Android devices out there. Do note, this obviously is in context of MediaTek devices, and a lot of bits are not open source. They're quite proprietary, so I cannot go too in depth. I can talk about the process, but not the technical bits of what actually happens. So yeah, let's get into the first thing, which is device security. What makes a device secure? When we talk about a device being secure, we're talking about the hardware and how it controls what runs on the device. We need to make sure the code is trusted, and we need to make sure if the code is not trusted, what do we tell the operating system, what do we tell the kernel about the device security status. If that's not handled properly, then well, you have false trust. You have a device that thinks the firmware thinks it's trusted, but it might be running malicious code. Further, a very big part of security is actually securing user data. If you lose your phone, what prevents someone from accessing the data on your phone? What prevents someone from, maybe installing some software on the phone that could do some sort of telemetry, track you perhaps, and you not realizing it, you lose your phone, install it with some malicious software, and return it back to you. I mean, Of course, this is not something that would probably ever happen to you, but this is a very common targeted attack, and we would like to minimize that as best as possible. And what does trust actually mean to applications that run on Android? So this is what device security is, securing data and securing the fact that the code that runs is not malicious. It is provided by the OEM. It is what is certified. It is what is allowed to run on that device. Guys, at any points, if you have questions, you can just unmute your mic and ask. I really don't mind you interrupting me, so please feel free, like loosen up. It's okay. So now, yeah, coming to the boot process, how does a MediaTek device start? We need to understand the boot process to actually know what parts are part of the trust process. So we'll first have a look into how the device starts up. So we have three fundamental units that we're going to be looking at. One is the SoC itself. This is the big package or chip that contains a lot of little components, includes all operational bits of your phone, your CPUs, your GPU, you have GPIO, so on and so forth, that your phone needs to run. One point of interest here is the ISRAM, which is your internal static RAM. And this will come in handy later when we talk about security. And there's a piece of code on the SoC. This is burnt into the SoC and cannot be updated, is the boot ROM. We'll discuss on what all of these do in a while. Then our second unit is the storage device itself. It can be eMMC or UFS. The standards change every day at this point. And our last point of interest is the DRAM, which is your regular memory. So your storage stores all the firmware. Your SoC is, think of it as the processor and everything else that the device actually needs to run. And the DRAM is your memory, basically, your RAM. So now we talk about when you hit the power button on your phone, the device needs to start up. What does it do first? So the SoC gets how much ever voltage it needs to get based on the package. Your boot ROM starts executing. This is a burnt-in piece of code. And it just performs a small, you can say, post. It does a self-check. It makes sure the hardware it needs, not everything else, just the what stuff it needs is good, and the device is not gonna kill itself if it tries turning on. It checks all that. Then if we go back to this slide, you will see there's two regions of our storage. One is in red. This is your boot sector. And the other is in green. This is called the user sector. So this is because your storage device is massive. And the boot ROM is a very small piece of code running at very slow speeds at very low voltages. It cannot, it'll take way too long to initialize the entire the entire storage device. So there's a fixed partition, which is a fixed sector called eMMC boot or UFS boot. And the boot ROM only initializes this. Now, another thing the boot ROM does, which is not as relevant to security in this startup context, is it listens for a flash tool over the UART port on the board and via USB, if there's a USB attached and supported. So what this allows you to do is, if the device does not have anything on the storage device, this allows you to flash any build, any software onto the device. And this has its own security measures, which we won't get into, which are quite proprietary. So yeah, boot ROM has now initialized eMMC boot or UFS boot. It has make sure the hardware looks okay, and it does all of its usual routines. Now, next thing the boot ROM does, why did it initialize UFS boot? It needs to load whatever is in UFS boot. So it's gonna pull preloader from that sector, and it's gonna put it into its internal static RAM. This is the highest level of trust, and since boot ROM is by default trusted, it needs to verify and make sure the preloader is fine, which is why it's not loaded into DRAM. Also because boot ROM is a very small piece of code and there's no way it can initialize DRAM at this point. So it has its own little memory and it uses that to allocate the preloader. There are two bootloaders on the device. I should have mentioned this earlier, which is the preloader and LK. We'll get into LK in just a second. So there's like two stages of boot. So now preloader is allocated, and the red dot on the side is showing you what is actually executing right now. So the boot ROM is executing. And now boot ROM will perform a jump to preloader. It does whatever security stuff it has to do. We'll get into the security bit of it in just a moment. And then once it verifies all that, it moves to preloader. And now preloader starts executing. What does the preloader do? Now, preloader is what does most of the work when it comes to initializing the hardware. It performs a complete post. It checks whether DRAM is okay, all voltage rails are correct. It initializes your DRAM, GPIO, PMIC, RTC, so on and so forth. It also initializes the rest of UFS, which will be necessary for booting the device, for doing anything you want to do on the device. And preloader is the second step of checking for a handshake from your flash tool in case, let's say you're at the factory and you want to install a firmware. Again, guys, this is limited to MediaTek devices. So other devices do things differently. Other devices handle trust differently. This is what happens on pretty much every MediaTek phone out there. So now, what does preloader do? Preloader allocates this thing called TEE. You might know this as trust zone. And your TEE partition contains, it primarily consists of two things. It consists of the proprietary OS. This can be a variety of things based on who actually designed the TEE. There are many vendors. And then there is a common layer called ATF, which is ARM trusted firmware. So again, we won't right now go into what TE and ATF actually does. That's in a later part of the presentation. But it is important to note that here on TE is what grants access for trust. So preloader will now load TEE and it will load LK. It will start executing TEE. TEE gets its own core, or maybe it has a discrete chip on the SoC, a trusted module. I mean, if you've upgraded to Windows 11, you might have heard about TPM requirements. That's the same concept, but not really. It can be either a part of your SoC, software, or it can be a discrete module. So we'll assume that TE is running on the SoC as a normal core. Our TE starts executing, and the yellow dot indicates that TE services are now available for use. The control is still on preloader, and preloader has allocated LK, which is little kernel. Little kernel is, you can think of it as U-boot, but highly proprietary and highly modified, and it consists code for A-boot, which is the Android bootloader. Again, this is context of Android MediaTek devices. There are other MediaTek ports that don't require A-boot. So LK is just, it works just like U-boot or microboot, however you call it. So yeah, now our LK is allocated. And now preloader needs to move on to LK. So it makes an SMC call. SMC is a secure monitor call. We'll get to that when we talk about EEE. And your TE does a few checks. It makes sure, hey, this address that you gave me, this looks totally okay. You can jump to this, and it's not some arbitrary address in DRAM that might be malicious. It checks all that. It checks to make sure that you're doing what you're supposed to do, and it returns whether you can continue or not. Once it gets the response, it actually performs the jump, and LK starts executing. LK is the actual bootloader. It does most of the work in terms of the security features that Android provides. So we're, for now, assuming that we have trust until this point. Then LK performs loading of all the firmwares, the little white, green box you see. This contains firmwares, your system image, or maybe a super image, whatever your Android configuration is. It loads, it even has your user data, which is read and write, to record all changes you do to the device. And after it has finished loading those firmwares, not obviously Android, Android is loaded by Linux. It just allocates your SoC, sorry, your platform specific firmwares. It allocates boot and RAM disk. So assuming here boot contains RAM disk, and this is what contains the Linux kernel. Your boot partition contains the Linux kernel, any parameters that go with it. It tells the kernel, hey, there's a RAM disk. RAM disk is at this address inside the boot image, allocate it, do your job. So LK reads the boot image, allocates everything, and then gets ready to hand control over to Linux. LK prepares to start Linux by issuing an SMC call. It has to tell the TE that, hey, you know what, we're going to be changing a trust level. It's called an EL exception level. And LK goes, yeah, okay, I know about that now. Let's head to Linux. LK jumps to Linux. It sets up Linux. Linux sets up. The first process of Linux is init. Init starts executing from RAM disk that loads all services necessary for Android. Yeah, sure.
Hello. Yeah. So I've been trying to follow, and you've said initialize and allocate a lot of times. Could you please explain what you mean by that?
So now, yeah, allocate and initialize are two different things. Allocation may be to memory, where when it loads something, let's say LK is allocating a firmware. So it will read that firmware, it will verify that firmware, and then it will allocate into memory. And then it passes the addresses of everything to Linux, or in case of most embedded devices, the Linux kernel already knows about what address it's supposed to expect because of DTS. So the point here is it just allocates things into memory. When we talk about initialization, let's say there is an X firmware partition that has been allocated by the bootloader, which is LK, and now Linux needs to actually make use of that firmware. So a Linux driver would then hit up that address, it would start executing that firmware, and it would initialize the hardware that that firmware goes on to. So yeah, I mean, they are interchangeable when you just casually talk about it, but yes, technically they're two different things. Thanks for pointing that out. Does that clear your question?
Okay. Yeah, like I was a little fuzzy on the initialize the hardware part. So like what, it sends power to that particular piece of hardware or something?
So it depends on what is being initialized. A lot of things are set up by LK. The hardware is all getting power, but yeah, it really comes down to what we're talking about. Like if we talk about, let's say, the display, right? Or we talk about the notification LED, which is a very simple thing. Many bootloaders allocate and initialize the LED as well. But then the kernel needs it too. So the kernel will deallocate it. It'll allocate it by itself if it needs to, if it requires doing that, and it will power up the hardware again. So yes, initialization does include powering up the hardware, but depending on what hardware we talk about, that hardware may already have a voltage rail that is on, and the hardware just isn't, the hardware response are just not being respected.
So if I were to use an analogy, allocation would be putting the data in a box, and then initialization would be using the box to actually do something.
Correct. Exactly. Initialization will use that box to execute code, and it will. How does it use that box? Of course, if the hardware is not powered up, comes down to the driver. It will power that up. If it's powered up, then well and good. Starts executing, does its job. So.
Yeah, that clears things up.
All right. Thanks. So, yeah, moving on. So now LK jumps to Linux. Yeah, this I've mentioned. Android boot up begins. In it loads all necessary services, and now one service is the Android's core service Zygote, and all related services in the vendor layer do their job. They initialize all hardware components. Maybe if we talk about hardware composer, the graphics allocator, managing GPU memory, and composing frames onto the device, writing to the frame buffer, so on and so forth. There's tons of services that do different things to bring Android together as what you see and use. So that all stems from init. Yeah, moving on. Now we are in Android, our device is booted, and you're using the phone. But now you must be asking, where is the security bit of it? Where's the trust bit of it? So let's talk about root of trust. And I'll be honest, guys, the line there, trust but verify, I had to put something there so the slide didn't look odd, but I could not think of anything, so I just looked up popular quotes about trust, and this is the only one that would fit. Yeah, this is. So we need to brush up on some concepts or know some concepts before we get into this. One such concept is eFuse, or one-time programmable memory. So this is a hardware chip where you can write data, but you can't unwrite data. So you have to be very careful on how you use it, even as a manufacturer, because once you burn an eFuse, remember, it's a fuse, it will burn. Once you burn something into the eFuse, you can only go forward from there. You can only modify the data such that your data is a factor of that and what you want to burn into it next. So small illustration here. This is how an eFuse looks like. You have substrate, you have a metal link onto it, and when you burn an eFuse, it literally burns away the metal and breaks the link. So the first diagram here is a 0, whereas the second diagram here is a 1. Now imagine an array of this creating factory burnt data. So this will come in handy in just a moment, like really soon. Now let's talk about MediaTek Secure Boot. And have you guys studied cryptography? Like, have you had the course yet? Can anyone?
Freshers haven't.
Okay, but I mean, are you guys familiar with, symmetric keys, asymmetric keys, so on and so forth?
Yeah.
Okay, that's great. So obviously here things are a little more dumbed down. They're slightly different on the actual device, but again, the specifics are quite proprietary. If any of you know me from before and you've followed my Redmi Note 8 Pro works, there's a Medium article, and that describes the fact that each partition was appended with two X509 certificates. And this is what they were. So when we are compiling, or when we're just putting together the software for the phone, we create a public-private key pair, which is generally RSA. And the private key is, we'll come to how the private key is programmed into eFuse later, but what we do is we can take the data of a partition, we can hash it, so RSA doesn't take too long, and then we can sign that data using a simple RSA encrypt with our private key. What this does is, if you know about keys, when you sign something with a private key and then you try to decrypt it with the public key, you get back your data, right? And vice versa. But we keep one key public and one key private. So here what we're doing is the device, let's assume the device knows of, the device has to verify that public key, and it can use that public key to verify that partition. How does it do that? The partition is signed with the private key, and when you decrypt the private key, when you decrypt the orange box, you get your hash of data, and you can very easily calculate the hash of your data on the device. And if they match, then you know the partition has not been tampered. So here, the hash function that's used is SHA-256, and RSA is RSA 2048. When we come to eFuse, we take the public key and we burn the hash of that into the eFuse. Again, remember, eFuse is only one-time programmable. So this is only burnt once and at the factory. This is to ensure that all the firmwares that load on the device are trusted, that they are only supplied by the OEM. And if any of Secure Boot checks firmwares, Android allows for loading modified firmwares, but it doesn't allow loading. I mean, it comes down to MediaTek, right? Android can let you load a GSI, which is a generic system image, but that's not checked by Secure Boot. That's checked by the bootloader. We'll come to bootloader in a second. I'm sorry, I'm getting off track here. So now let's talk about a little more detail on how the verification actually happens using our boot flow, again, our boot sequence. So boot ROM is burnt into the SoC. Remember I said that it is trusted. So we don't have to check boot ROM for trust again, because there's really no point of doing that. No one can simply burn a new boot ROM onto the chip. So now when boot ROM starts executing, it needs to load the preloader. How does it know the preloader is a preloader that the device can run, that is made by the OEM? Remember here, imagine this data is the preloader, but this entire thing is the preloader partition. The data inside is the actual preloader executable. And here you have cert1 and cert2. So it will first check cert2, the red box. It will hash that, and it will compare that to eFuse. Remember, we had burned our public key, the hash of our public key into the eFuse. It first checks that to make sure the public key is trusted, if the public key matches what's programmed onto the device. Once it knows the public key is true, then it will perform a decryption on the cert1. So when it performs decrypt, it basically takes cert1, comma, your public key. So that effectively gives you hash of your preloader data. PL in blue is the executable of your preloader. So then now you have a trusted answer to what the hash of your preloader will be. And you can simply perform a hash of the actual preloader data and make sure they match. If they don't match, you know the preloader has been tampered and you cannot continue executing it. But if it hasn't been tampered, then you know, hey, this checks out with the public key that's supplied on the preloader, and it checks out with the public keys hash that is programmed into eFuse. So we know that we can trust it. Let us load it and let us start executing it. Preloader is now loaded into the SoC memory. Then preloader has, I mean, this is again going a little in depth, but it has a security config. It's basically a giant header, which tells it what it needs to check with MediaTek Secure Boot. Preloader, if the security config says that preloader needs to be checked, although this is just an extra step, this is not necessary, it will verify itself. And further, it will verify the TEE partition, because remember, TEE is what performs loading of LK. It is what's required for loading LK. So it needs to allocate LK and TEE, your little kernel and your trust zone. So it loads both of them. It verifies both of them the same way. They are also appended with the hash of the data signed with your private key and the public key. Performs the same operation, makes sure they're fine, and then allocates them into DRAM. Once it is able to verify the security configuration, it makes the SMC call to trust zone to jump to your little kernel, which is bootloader. In this SMC call, it also passes the security config, because now the bootloader needs to know what sboot needs to go on for the remaining firmwares, because remember, it needs to trust all firmwares that run on the device, because they could be running on components of the SoC which have direct access to CPU registers. Now you notice on this slide, there is text that says EL3 on top of the SoC. Remember how I mentioned this is the highest level of trust. So there are 4 levels of trust: EL3, EL2, EL1, and EL0. 3 being the highest, 0 being the lowest. So the SoC is considered EL3. Your preloader, your boot ROM, they're all EL3. Even your TEE is considered EL3 because it's what is used to gain trust. Even though it is allocated in DRAM, it is verified before it executes or does anything. Now, LK, remember the SMC call that was made to jump to LK? It uses the security config from that. It verifies all the firmware partitions it needs to. Maybe there's CAM VPU, SCP, there's so many firmware partitions. Then it queries the device state. You remember how I mentioned Google lets you load a custom version of Android onto every phone if your manufacturer is okay with it. So, for example, loading a GSI or loading a custom ROM. So the bootloader, again, a custom ROM could still contain software that is tampered or malicious. So there's no way the device can simply trust it. If the device trusted it, the user would think it's running safe software, which it potentially isn't. Imagine there's a middleman who's installing a custom ROM onto a phone with malicious software and reselling it to the end user, which is extremely dangerous. So your bootloader will read the state. It will, this is usually stored in an entity called sec.config, sec.cfg, which is nothing but a partition on the device. It reads that based on the device state, it decides whether it needs to actually verify the Android image or not. If the bootloader is unlocked, it even shows a warning on the screen. If any of you have played with custom ROMs, you might have noticed on the boot screen, you either have an unlock icon or you have some text that says this device is unlocked, cannot be trusted, or just a giant screen that says yellow state, this device cannot be trusted and your OS will boot in 5 seconds. That's what the unlock bootloader is. That's what the bootloader is doing. It is telling the user that this software is not trusted. So this is where I mentioned handling of unsigned software. You can run unsigned software, but that software is only Android and not the underlying firmware partitions. Though it should be mentioned, there are security configs to allow unsigned firmwares to boot as well, minus the preloader. Preloader is EL3 and it will always have to be signed and trusted. It cannot be recompiled and loaded onto any device. So our sec.cfg is loaded, shows the warning. It verifies each firmware partition using the same as boot method. And then if, let's say, device is unlocked, it will append a command line that says device boot state is orange or yellow or red. Each of them have different meanings. The trusted state is green. Surprise, surprise. So it also makes an SMC call to TE to store various security identifiers. This is before it tells it that it's jumping to Linux and that is a change to EL1. This SMC call basically will store things such as there's a lot of security identifiers on Android, such as your security patch level, that are often used to determine how to handle encryption. Features like anti-rollback of user data is all controlled by this. So the bootloader reads all those properties from various partitions and it writes that to TEE via an SMC call. Now TEE remembers it, and when Android does start executing, Android with underlying vendor services can look this value up and decide what to do. So that's what Android verified boot is. And Android verified boot is much more, but this is one feature of Android verified boot. And it also stores things like whether the device has been unlocked and a lot of other security configurations. And yeah, so EL2 is hypervisor, and most MediaTek devices don't have a hypervisor, don't need a hypervisor. I think the only devices I've seen are with a hypervisor are like Samsung devices. which have Knox, and Knox has a hypervisor to basically check real-time kernel tampering if someone's somehow writing code into kernel memory and changing what the kernel is supposed to be doing. But MediaTek devices and I think even Qualcomm devices don't have a discrete hypervisor. So EL2 is completely optional. We have EL3, which is our SoC, EL1, which is our bootloader and the Linux image, and EL0, which is the least trusted bit, which is the user land or user space, which is Android. So now we talk about TEE. Let's say Android has booted up, Android is trusted. How do applications actually use TEE? And what actually goes on in a TEE? So, excuse me, we have two things, your trusted execution environment, TEE, and a rich execution environment. Rich execution environment includes your everything after EL1. After EL1. So EL1 and EL3, which is Linux and the Android operating system itself. Now, let's say you are unlocking your phone, right? Your settings app or your lock screen, which is system UI, will have to perform an authentication. The actual key of your biometric data is stored inside TEE. It's stored inside the storage of TEE, which is RPMB, or Replay Protected Memory Block. So how does it do that? There are several APIs that lead to an underlying layer called Keymaster. And Keymaster can be considered as a CA or client application. This will then request that, hey, I want the services of the Keymaster TA, which is a trusted application inside TEE. And it gives it parameters. I want this. Here is the data I give you. Tell me if this data is correct. Remember, TEE will never spew out data it has recorded. It will tell you whether data is valid or not. It's kind of like attesting whether things you have told it in the past match up with what you're telling it now. So there is a kernel driver which will interact with the ATF monitor. The monitor is the common layer between TEE and REE. And this monitor keeps listening for calls from both worlds, your insecure and secure world, secure being TEE and insecure being REE, rich execution environment. So your kernel driver says, hey, this looks okay. We're going to do a client API call. We're going to handle this client API call by issuing an SMC call, which is a secure monitor call. Remember, monitor. And it issues a call to ATF. Now, ATF handles this SMC call it issues an SMC call by itself to talk to the actual TEE operating system. This is a proprietary layer. ATF is quite open. There are many projects, most notably OPTEE or OpenTEE, which implement a TEE OS that runs on ATF. So ATF makes an SMC call to the TEE OS, and then this uses the trusted application to do what it's supposed to do. If it needs to check a biometric, it will receive the data, it will compare that and tell you if it's okay or not. So this is how your rich world and your secure world talk to each other. Now, the final thing is the features that Android and Linux that are common to all devices. Sure, we've talked about trust zone, which is also pretty common. But when we talk about trusting the device, whether the code is executing is correct or safe or not, there are several security features on the Android and Linux side, which make sure that the device is not tampered, or if it's tampered, it's doing what it's supposed to do when it's tampered. First is DM Verity, an Android verified boot. I've mentioned verified boot before, but it allows you to basically verify partitions. It's basically cryptographic checks to tell you if the partition integrity is not broken. not going to go too much into that. There's a great article on Google's source.android.com. Your bootloader lock and unlock states. Whenever you lock a bootloader or unlock a bootloader, you're changing whether it can run trusted or untrusted software. So naturally, it makes sense that we have to erase all user data on the device, because if user data is not erased, the bootloader might allow loading a malicious firmware, which is now able to access all the data on the device. So we don't want that, and we're going to destroy all data when there's a state change. Further, when the bootloader is locked or unlocked, it reports to the Linux kernel via command line and via trust zone. And then different services on Android can then look this up and know whether the device is running stock software or OEM software. And based on that, if you've played with custom ROMs, you would know about safety net, which checks whether the device is certified with Google and whether the device is secure, to make sure the device is compliant, or the software running on the device is compliant. And if safety net doesn't pass, you will actually see many apps, including banking apps, fail. Of course, there are workarounds. It's a constant cat and mouse game. That's why security is such an awesome topic. It changes every single day. Then user data is mandatorily encrypted. Google does not allow certification of devices anymore that do not encrypt user data. And Google now allows for hardware-backed storage, which again is TEE and RPMB, so storing sensitive keys or information inside of an entity that cannot be easily tampered with inside a secure space. And finally, Google is very strict about certification. If you don't certify a device, it's going to fail safety net. It's going to lose out on some features. There are two levels of GMS certification. One is the device being certified, and one is an update being certified. If the device is not certified, you can't run Google services outright. Android is borderline unusable. Many people consider it unusable. There are alternatives to Google services, but frankly, they're obviously not as complete as a massive company providing services to use a phone. Further, with certification, Android also allows for security compliance testing, which changes on a monthly basis. If you open your phone and you go to About Phone or you go to Security, you will see something called a security patch level. That tells you until which month, until which specification have the security patches been applied to your phone. This way you can identify what exploits would your phone be vulnerable to, and it comes down to the manufacturer to issue these updates. While Google is working on streamlining all security updates, so it comes under the Google umbrella, and the OEMs like us don't have to worry about it, it's still quite a long way. And the newer your security patch, the more secure your device is, the more susceptible it is to actual real-life exploits. And almost all vulnerabilities are publicly disclosed, except ones that are too critical, which are given in confidence to all partners. And if, let's say I'm a partner who doesn't have access to these resources, I cannot pass these tests, and further, I cannot certify my device. So that's where certification and security compliance testing is extremely useful. I mean, of course, it's a lot of work for us, but it's a great thing for you guys as users. So finally, conclusion time. Every device implements extremely different low-level security features. This is just what a very high-level view of what MediaTek devices do. The fundamentals are pretty much the same on how trust is gained, what parts are trusted, what shouldn't be trusted, how verified boot works, how security checks inside Android work, how trust zone works. The security model is already quite in-depth. It's already quite incredible, but it is not perfect. I mean, a good example is the boot ROM. The boot ROM doesn't check whether it is trusted, but if someone did have the skills, or if someone was able to somehow swap out boot ROM, because to this day, I don't know a single person who knows how boot ROMs actually stored on the SoC. then a modification to boot ROM can be quite disastrous, because then it lets you load a modified preloader, further a modified bootloader, Linux, so on and so forth, and make it appear as a completely trusted chain of events. So root of trust is not really there. And yeah, security standards are always changing. Guys, don't limit yourself to what you see right now. Keep looking things up, keep seeing what devices do. Listen to manufacturers, or listen to researchers when they say, hey, there's new security implementation. You will see this on your phones soon. Study what different devices have to offer. Of course, it's not marketing. It doesn't come under marketing, talking about how actually secure devices, but it's not that hard to figure out, especially if you like tinkering and if you can take stuff apart, take software apart and see what's actually inside. So yeah, that's it for me. Any questions? Any doubts? I mean, I know it was a lot of information, but I'm sure this is being recorded and you can replay this. Reach out to me whenever.
If we want to actually find like the CVEs, the actual CVE, is there like an aggregate site or something, or do we go to like each individual resource?
So, I mean, okay, here's a funny story. When we talk about looking up CVEs, for a while, we actually did not have a lot of resources when it came to security testing. So we would encounter security failures and we would not know how to patch them. And in my development cycles, I've noticed the easiest way to identify those patches is through a Google search. You just Google CVE ID. There are lots of websites that keep a track of them. You might not outright get the patches, but it tells you about related components, and then you can ask your partner. We talk to a partner for these resources. We talk to a partner, tell them the CVE number. We tell them this is the component that we need the patch for, and they provide us the change, and we apply that change. So looking up CVEs, a simple Google search, that's more than enough. Further, all CVE IDs are always listed in each Android security bulletin, so you can look them up there as well.
Okay, yeah.
Anything else?
I did another question. If somebody wants to create or modify any of the modifiable structures, or like make their own signed and verified firmware on that particular stage, what tools do they use? Programming in C, or are there other like stacks that you can use?
So you can't really have a modified firmware and sign it to run securely. That's the first thing. The private key I mentioned, of the private and public key pair, the private key is private to the manufacturer, and we do not disclose this for obvious reasons. However, let's say you are signing things by yourself. There are devices that support signing stuff by yourself and verifying your signature. That is certainly doable. And to do that, it really comes down to the device. There are proprietary tools, but other than that, when it comes to checking the actually verifying signatures, that's it depends on the component. If we talk about the preloader and we talk about the little kernel, they're both in C. So C and assembly. In fact, a lot of secure boot code is not even revealed to us as manufacturers. They are present as pre-built objects inside a BSP, or board support package. And almost all this information was understood over the months, over the weeks, by reverse engineering, by identifying what's actually in there. So to answer your question, yes, I mean, the primary language that was used is C, but when it comes to secure boot and verifying, it's really just your cryptographic keys, and it really isn't specific to any language or framework.
Okay, yeah.
Any more questions?
Any other questions? Yeah, please.
So you've explained this from like a developer's point of view. What about the attacker's point of view? What if somebody actually wants to break into this? Create a vulnerability for themselves or find one that exists. How would they approach?
So that's a really good question. When from a point of view of an attacker, obviously I can't give you a lot of context because I like to study security. I do like to tinker with it, but I haven't really tried doing a lot of exploits. But from an attacker's point of view, I think the first most obvious point of attack vector would be vulnerability of the cryptographic implementation itself. And most common vulnerabilities include any sort of interaction with memory, because more often than not, you can, through hardware, through software, through modified code, you can try to read, dump, modify, and execute parts of memory. If you can make memory behave in a funny way, you can make it jump to, if you can find like the execution pointer, for instance, you can make it jump to whatever you want if you make your memory act funny, right? So from an attacker's point of view, it's there's a whole lot to consider, and it comes down to what you're attacking and what you want to gain out of it. On a MediaTek device, if you want to attack the boot process, I think an exploit into boot ROM is great. In fact, someone has actually exploited several boot ROMs of MediaTek devices, wherein it basically allows you to turn off some security checks for flashing the device. However, it doesn't replace boot ROM because it's burnt onto the chip. Other ways of attacking could be somehow, one other attack that is known is not really even an attack. It was basically a leaked bootloader that had many security configurations turned off. So it's still supported by the device, but it can do a lot more. So yeah, I'm not sure I can answer that question too well, but there's it really comes down to what you have on your plate and what you really want to do with it.
Okay.
All right, so I think we can wrap this up right now.
Any other questions? Anything else? Anything. It's okay. Like, there's no questions that are stupid. Just fire away.
You had mentioned the BSP. Can you where do you get the BSP? Is there one ready-made? Is like you said you reverse engineered some, so there definitely be some that aren't reverse, right?
So the BSP isn't reverse engineered. I was talking about understanding how secure boot works. That was reverse engineered. But when it comes to the BSP is provided by a partner. But really, a BSP could be called anything that produces the stock software that goes onto your phone. You could be making a BSP yourself if you have all the relevant code. A good example is we took our Android 9 code base and turned it into an Android 10 BSP using upstream AOSP code. So the BSP, certainly the best BSPs, they come from our partners. When we don't get something from our partners in reasonable time, we take things into our own hands and we develop our own BSPs. So yeah.
Okay, so is this like upgradable over the air or?
The BSP is just code. So really, when it comes to over-the-air updates, that comes down to us using that code to create an update that we can ship to users. Of course, there's a lot of testing that is necessary to make sure that when we create an update, it applies correctly to what the users already have. It doesn't break any components. The partition table matches. The kernel does what it's supposed to. It does everything it's supposed to on that hardware and can be certified. So in terms of over the air, the BSP doesn't come over the air. It's just a new BSP with new code, new software, new hardware layers, new kernels, so on and so forth. And really, it comes down to us to actually use that BSP to make an update that can ship to users over the air.
Okay, yeah. So the BSP is like a skeleton that you get, and you build your own framework on top of it and keep it out.
Sort of, yes. I mean, it's the board support package, so it has all the code we need to run a new version of Android, say, on that board or on that product. We make certain changes for things that are different on a device compared to the sample device that, let's say, MediaTek provides. There's a sample device or a reference device, and there is our device, which is a subset, or in some cases even a superset, where you add more features onto it of that reference device. So the BSP is of that reference device, and we need to know what we need to change, what we need to add to make it run properly on our phone. So it is basically, you can say 90% of what you need to create an update, but the 10% is basically you figuring out any changes that need to go on for your product.
Cool, got it. Yeah.
Any more? Any other questions?
When you were talking about an application like the phone unlock screen pattern for the biometrics, right? Any application just for anything, or is there something like access permissions, like we have read write access permissions in Linux operating systems, right? So suppose like an application asks for location permission on my device, and suppose I grant it, right? Is it only then that application can actually do the whole thing, or can it still send requests even when the permission is not approved?
Okay, great question. So that comes down to the Android API. And when it comes to permissions, it's up to the Android framework to manage these permissions. Of course, if a permission is not granted, Android will not permit that app to, let's say, use location or camera. In fact, with recent versions of Android, even when you grant an app, let's say, location or camera services, permissions, there are simple toggles to completely turn off camera, to completely turn off location for all apps across the board. So it's not as simple as Linux permissions. Linux permissions are certainly there, but they're for different purposes. Let's say, labeling kernel nodes. I mean, not labeling, like setting permissions and control on kernel nodes to what? To only allow what is supposed to be allowed. Further, when you talk
example,
about, yeah, go on.
yeah, a simple example that I had in mind, an example that I had that got this question was basically when I open an application and the initial open, it asked me permission like while using the app only, allow permissions only while using the app. So
Yeah.
I'm curious, when you allow it, what's the difference between only while using the app versus when the app is in the background, and like versus when you're allowing it always?
So an app has several states. Again, you mentioned background. There's foreground and background. When you allow an app to only use location while in the app, Android will basically check two things: whether the process is created and whether the process is in foreground. If it's in foreground, it will allow all requests it makes for location. Otherwise, it will simply deny them. In background, the app may make requests, but it will just not receive any responses. It will just receive an exception. And
This is
I mean,
actually doesn't
yeah.
the entire process that you've described. This is just what you described is after the Android API, and what I'm talking about is
Yes.
before it enters the API. Cool.
Yeah,
got
so
it.
what you're talking about is Android itself. I was talking about everything below that. So Android in itself has a lot of security rules. Linux implements a lot of security rules. Another thing I probably didn't mention in my presentation was SE Linux. When you talked about permissions, Linux permissions, there is another thing which is security enhanced Linux. And this allows you to create a set of rules that uh, basically give you very granular control on what parts of, let's say, what apps, what services, mostly services. It's very rare that we label individual apps, but what services can access what files, what can they read, write, execute, IOCTL, open a socket to, relabel, so on and so forth. There's there's a ton of rules. This was first introduced by Samsung. This became a part of the Android specification from Android 4.4, KitKat, and it's stuck with Android ever since. It's just getting better and better with each release, more secure, more of, services only do what they're allowed to do.
Okay. Yeah.
Anything else? One last question. Let's go. Is that all?
I think it is.
All right, sounds good.
So I think we can wrap this up now. So this was a really informative lecture. Thank you for coming. I would like to extend my sincere gratitude to you for taking out the time and coming to our university's class. So I hope your session would help incite and spark that innovation and curiosity in people, so we could become
hope so
better
too.
contributors. Right. So thank you for coming.
Thank you guys. Thanks for being awesome. If you need to reach out to me, you can just hit up Gagan. He'll give you my contact details. Don't hesitate on asking questions. Just let me know where you're from and the question you have, and I'd be happy to answer it. Thank you.
Thank you. This was a really fun session.
All right.